Today we're going to begin the final unit of the year. We are going to be looking at moving charges using magnetism. This is going to be a really important idea in the history of humanity, and so much of our modern world works off of this idea. So we want to take it slow. Today I just want to introduce you to the idea. We'll do some labs on it coming up, and then eventually you'll get hopefully pretty good at understanding how we can use magnetism to make charges move. So here is our goal for the unit. You should probably draw this out just so you have a little sense of what we're trying to do. So we're going to take a charge like an electron that is at rest, and we're going to try to use magnetism to get this electron to move. So somehow we need to get charges to move using magnetism. That is the goal of the unit. And it seems so easy. You just put the electron near a magnet and it should move. But if we think about what we just learned in the previous unit, we can see that that's not going to be true. Because when we have a charge at rest, we saw that no force is generated from the magnetic field. We had a formula that said force magnetism equals QVB, and if the velocity of this thing is 0, we're never going to get it to move because we don't have any magnetic force to move it. We learned that when it was moving, there is a force, but the problem is that force just deflects it. It doesn't speed it up. We can't use the magnetic field to make this charge move faster. All we can do is deflect it. That's not going to be helpful. We want to be able to get this charge to start moving or maybe to speed it up. Okay, so what we learned in the last unit will not work. So let's review what we learned in the last unit because it is going to be helpful for understanding what happens in this unit. So the big idea from the last unit was that when charges are in motion, they create a magnetic field. I would like you to have that in today's notes because it is the important idea on which this unit will be based too. Okay, so one more time. Moving charges create magnetic fields. Moving charges create magnetic fields. We did a lab on this where we moved some electrons through a wire and we looked at how strong the magnetic field was going to be around the wire. That's one of the last things we did in the previous unit. Moving charges create magnetic fields. We can apply this to different gadgets, and I don't need you to know a lot of the details of these gadgets. I would like you to just write down some of the ideas, though. So that idea from the last unit, that moving charges create magnetic fields, can be used in things like electric motors. We can generate by running electricity through our coils. We can create an artificial magnet, which will then interact with real magnets to cause the coils to spin. This was our electric motor. This is going to be the heart of all of your power tools, all kinds of gadgets in your kitchen, like blenders and mixers. It's going to be the heart of things like our modern electric cars. So it's an important idea from the previous unit that these moving charges, these currents, create magnetic fields. Magnetic fields can interact with other magnetic fields and cause forces. So just make sure you know an application of this was the electric motor. Another application is the speaker, where we can have a coil inside our speaker or our headphones. We run electricity through it. It generates an artificial electromagnet, which causes the coil to move, which causes the speaker to move, which causes sound to come out of the cone of the speaker. Okay, so that's another application. You don't have to draw it. Just know another application of our previous unit is the speaker. Another application is the doorbell, where we have our coils of wire in here. We run electricity through the coils. They create a magnetic field. They pull the striker down, hits the bar, creates a sound. You let go of the doorbell, the spring shoots it back up, it makes another sound. Again, you don't need to know all the details. It's just another example of us using currents to create magnetic fields to do jobs for us. The final one we did not talk about before, so I would like you to write this one down. This is called a railgun. And with a railgun, we're going to try to use what we learned in the last unit to fire a metal projectile. So the way a railgun works is like this. If you could draw this out, you have a battery, you have a set of rails, and those rails are not connected to each other. So you have no electric circuit, you have no electricity flowing through the system until you drop a metal bar onto the rails. And when you drop that metal bar onto the rails, you get a complete circuit. And electricity will flow through the rails. More importantly, electricity will flow through this metal bar. And as electricity flows through that metal bar, it generates a magnetic field. That magnetic field interacts with a pre-existing magnetic field. So all these X's are from some kind of external magnet, okay? And that external magnet makes a magnetic field. It interacts with the magnetic field in this piece of metal, and those two magnetic fields generate a force that is going to push this bar either to the right or to the left. It's going to accelerate as it moves along the rails, and if you have enough current and a strong enough field, you can get this bar going at amazingly high speeds. Here's an example of one where the speeds are not amazing. This is my system. We got the metal bar. We got our rails. Underneath the rails, we have magnets that you can't see that generate a magnetic field. And then on the other side, again, you can't see it yet, we're going to have one side hooked to negative and one side hooked to positive. Right now, there's no electricity flowing through the system because the metal bar is not actually touching the rails yet. When we drop it onto the rails, you'll hear the electrical sparks and you'll see the metal bar, metal roller actually in this case, pushed to the right. If we reverse the electricity, it would have been shot to the left. All right, so the big idea here with the railgun is we're turning electricity into motion using magnetic fields. The electricity is what we start with, and the motion is what we end with. In this unit that we're about to start, we're going to try to reverse this entire process. We're going to try to have electricity as our product. Electricity is what we're going to try to produce from the magnetic field. So that is our goal. And this goal has a name. It's called induction. We are going to try to induce currents to flow through a wire using a magnetic field. We're going to, again, induce currents to flow through a wire using a magnetic field. We're not going to use batteries. We're not going to have chemical reactions. We're going to have this current flowing through the wire from magnetic fields. We're going to induce the current with a magnetic field. It's called induction. And real quickly, I don't want to do too much of it today, but I do want you to see the start of this. The best way I think for you to think about how this happens is to imagine our railgun, but for the moment, let's get rid of the rails and let's get rid of the battery. We're going to get rid of the battery altogether. We want to have no battery. We want to have this electricity be produced from us and the magnetic field. So you have your metal bar. We're going to pull it or push it through the magnetic field, as you can see in the picture, and we're going to see what happens. It's important to remember that this metal bar is neutral. So it's got positive and negative charges inside of it from the very get-go. All matter is neutral, but all matter has a balance of charges. It's also important to remember that only the negative charges are able to move. So when we push this bar through the magnetic field, the negative charges are going to be pushed toward the top of the bar. How do we know that? We use our left hand rule, where our fingers point in the direction of the magnetic field, our thumb points in the direction of the motion of the bar, which would be in this case to the left, and the force magnetism, our palm is going to push toward the top of the bar, so the electrons are going to be pushed toward the top. If we use the right-hand rule, we would see positives getting pushed toward the bottom of the bar, but we know that the positives are locked in place. The protons are part of the nucleus and they cannot move. So the electrons move to the top, the protons stay where they were. That leads to a separation of charges, where the top of the bar has more negatives than it does positives. It still has positive charges there, but it's got an excess of negatives. The bottom of the bar is going to have an excess of positives, not because the positives moved there, but the negatives that were at the bottom were forced to the top. So we get the separation of charges simply by pushing a metal bar through the magnetic field. I hope you realize that as soon as we stop moving the bar, the negatives are going to rush right back to the positives because they attract each other. Again, the positives can't move, but the negatives can. So the separation of charges only exists while we are pushing the bar through the field. Now we're going to set down some rails, but instead of having a battery, we're going to put a light. Now, when the bar is moving and the negatives move to the top, they have a pathway that they can follow to get to those positive charges. They cannot move back down the bar because the magnetic force is pushing them toward the top. Okay, but they can move through the rails, move through the wire, and move through the light. And when they do that, they will light up this light bulb. And we will have created electricity, not by using a battery, but simply by pushing this bar through the magnetic field. We will have generated a current. We will have induced a current. And what we're going to try and do over the next few days is we're going to do a little lab where we try to determine the factors that determine how much current and how much voltage we're going to generate as we push this metal bar through the magnetic field. And that's where I want to leave off today. We will eventually learn more about what's happening. We'll generate some formulas. We'll see all kinds of different places where we use this in real life. But for now, I want you to understand the goal and the basics on how we get this to happen.